Is it working now? Yes, it is. No, this isn't going to be a regular talk at all. I just wanted to give a brief appreciation of Hans Duistermaat's work. He was to lecture in last week's Poisson School, but he died a few months ago. He knew he was suffering from cancer, and he was undergoing chemotherapy, which, as you probably know, suppresses the immune system. And he contracted a pneumonia, and the complications of that carried him off. Here's a part of his mathematical heritage, according to the Math Genealogy site. Like quite a few of us, he's descended from Gauss. When you've seen this long line of Germans, you may think that he went to Germany for his PhD, but he didn't. Freudenthal came to Amsterdam to work with Brouwer. That's the fixed point Brouwer, not the Brouwer group Brouwer, who was German. It seems that Freudenthal and Brouwer didn't get along too well, and anyway, after the war, Freudenthal ended up in Utrecht. And I think it's fair to say that it was Freudenthal who put Utrecht on the map as a quality mathematics department. He attracted good students and collaborators. Duistermaat had 23 students. I'm one of them. And I promised a discussion of his contributions to Poisson Geometry. Well, in a narrow sense, he didn't make any. I don't think he used the word Poisson manifold anywhere in his written work. Poisson brackets are a different matter. Duistermaat was basically a differential equations man, though with an unusual geometric insight. Perhaps his best-known work to geometers is the Duistermaat-Heckman theorem, of which you can find many expositions in textbooks by now. I won't be talking about that. I'd like to discuss 2 or 3 things that maybe is a little bit less known to at least some of you. One of those is a long paper with Gilliman on spectral theory. The setting is out of a compact manifold, n-dimensional, and you have an elliptic pseudo-differential operator of order 1. Positive self-adjoint. Now the example to keep in mind is that of the Laplacian, which however is second order, but you want to take the square root of that for technical reasons having to do with convergence of certain asymptotic expansions. So you take the square root just in this spectral, by using a spectral resolution. You pretend this Laplace is a very large matrix. You diagonalize and you just take square root of all the eigenvalues. Then you have a first order operator. Of course, what we're interested in is the eigenvalues and the distribution of the eigenvalues. And of course, those of P and the Laplace are obviously related. P is no longer a differential operator here. It's a pseudo-differential operator. It's not, after Fourier transform, it's no longer given by multiplication by a polynomial, but by a more complicated symbol with a nice asymptotic expansion. So that symbol I will call little p. It's a function on the punctured cotangent bundle, the principal symbol. And of course, instinctively, we also look at the Hamiltonian vector field of that principal symbol, h of p. I'll call the eigenvalues lambda I. So they're all positive. They form an infinite sequence going to infinity. And to collect all that information, I'll just place a delta function at each eigenvalue and add up all those delta functions. That gives me the spectral distribution. So in the case of the Laplace, this symbol will just be the length of the cotangent vector. And the Hamiltonian flow up to some constant would just be the geodesic flow. Now, one may want to think of P as a quantization of a classical object, observable P. And in a talk devoted to Hans Duistermaat, I cannot use such language with a straight face. Duistermaat never used such talk. I mean, many mathematicians like to think in terms of big ideas or meta-mathematical theorems or deep analogies with physics. Duistermaat's mind worked in a different way. One way in which he did work was by being gregarious, by talking left and right to people and finding out what interesting problems are and helping those people solve their problems, or not infrequently, beating them by solving their problems for them. When he began working with Duistermaat, he warned him, with Gilliman, Victor Gilliman, I mean, he warned him that I'm a fishy character to work with. Duister is dark, maat is mate. So it's an untrustworthy friend. Also, as a little boy, Duistermaat lived in the then Dutch East Indies, now Indonesia. And he told me one of his entertainments was to go flying kites with the local lads. The practice was to attach razor blades to the lines. So winning the game wasn't just a matter of getting your kite high up as possible, but also of cutting loose your opponents. I mean, okay. What? Okay. One can read too much into these things, but to me they reflect some of the man's spirit. Nevertheless, there is this analogy in classical and quantum, and an equilibrium state of the quantum object, of the operator P, that is, it would be an eigenvector, an eigenstate. Whereas the equilibrium state of the symbol of the function would be periodic orbit of its Hamiltonian vector field. So one might expect some relation between these two things. And that's what the paper is about. So let's take this symbol and let's Fourier transform it. So these delta functions become exponentials. And one useful thing is that this is a tempered distribution. It doesn't go too fast at infinity, and therefore so was the original spectral distribution. And you may also want to think of it as a trace of a certain operator. Because lambda is is the eigenvalue of P, then e to the I lambda t is an eigenvalue, obviously, of the operator e to the minus itp. And that's a unitary operator. And the transformed spectral distribution is the trace of that, distributional trace. And we're going to see formulas for that, which are asymptotic, and which are collectively known as semi-classical trace formulas. Okay, the first theorem then is that, this distribution is really a function, a smooth function, except where you have periodic trajectories. So the spectral variable, I will call it lambda, the transformed distribution is then a distribution in a variable I'll call t. And its singularities occur only for those values of t which are periods of periodic orbits. So that's already one way in which the operator detects equilibrium states of the Hamiltonian system. So then, of course, you want to understand the singularities of this spectral distribution. well, first of all, every orbit can be seen as periodic zero, so you expect a huge singularity at 0. And to zoom in on it, let me take a function chi of lambda, whose Fourier transform is a little bump function supported near 0. And let me multiply my transformed spectral distribution with that. Well, then that's an obvious calculation. Multiply this Fourier transform by this exponential. That means that you get the Fourier transform of the shifted functions. And instead of giving a formula for the singularity at 0 of sigma hat, I'm just going to give a formula for the thing inside this Fourier transform. That's equivalent. And the thing is that there's an asymptotic expansion for this as the spectral variable goes to infinity in terms of these powers of lambda. And these constants, Gilliman and Dijkstraat have expressions for them. The leading coefficient is the volume of the unit sphere. This P was an elliptic symbol, so setting P equal to 1 gives you something like a unit sphere bundle in the cotangent bundle. And the leading coefficient is its volume. Now, if you integrate this left-hand side, then that's the value of the Fourier transform chi hat at 0. So that's 1. So then you're going to get a 1 for every eigenvalue on the left-hand side. So that gives you the number of eigenvalues, which of course is infinite. So instead, an interesting thing to do is take this left-hand side and integrate from minus infinity to some fixed value lambda. And then you expect to find something related to all the eigenvalues less than or equal to lambda. And let me give a name to that number. Let me give it NP of lambda. That's the counting function for the eigenvalues. And by doing a little bit of analysis with this, by fooling around with that asymptotic expansion, you get a formula for that, an asymptotic formula. That number of eigenvalues grows as lambda to the n. That is Weyl's law. Weyl found this for the Laplace in a domain in R2 and R3, I think. Weyl was inspired directly by Planck's paper about the black body radiation. So this is a generalization of that. And the leading coefficient here is the volume of the sub-level set, where the principal symbol is less than or equal to 1. So here you see that the classical notion of a volume is directly related, asymptotically, to this quantum notion of the number of eigenvalues in a certain region. Gilliman and Dijkstraat they have several refinements of this. I think they have formulas for the for the next term in this expansion too, and several other things, like instead of counting the eigenvalues, you might do things like for every pair of eigenvalues, lambda j, lambda k, look at the difference and look at how that set of numbers distributes. And they have results about that too. Now, much of the analysis for this singularity at 0 of the Fourier transformed spectral distribution had already been done by Hermander. Gilliman and Dijkstraat also looked at the singularities at the non-zero periods. And you get a similar you can do a similar cutoff and get a similar asymptotic expansion. And from that, by doing that, they've come up with the following statement. The transformed spectral distribution at these periods is almost like a pole, as if it was a meromorphic function. And there's a formula for the residue of that pole. If t is a period, a non-zero period, then the residue is a sum over, well, all orbits of that period, t. And the expression inside, the t naught gamma, that's the primitive period of that orbit gamma, so the least period. And this m gamma is a certain integer called the Maslov index. And in the numerator, the denominator, you have the determinant of 1 minus the Poincaré return map. I guess this picture is quite familiar. If you have a periodic orbit, you look at a little transverse slice, and you get a germ of a map by looking at a sufficiently close point and seeing where it returns. That's the Poincaré return map. And the assumption in the theorem is that it does no eigenvalue equal to 1, so that this denominator makes sense. Note, by the way, there's more than a passing resemblance here to the Atiyah-Bott Lefschetz formula for elliptic complexes and maps on elliptic complexes, which has a similar sum. But that's an exact formula, not an asymptotic, not a limit formula. This funny integer m lambda, you can also see it as something that comes from a variational problem, a Morse index. A so-called Conley-Zehnder index. I think for general operators that connection was made in an early paper by Eckhard Meinrenke. Although that was long known to be true for the geodesic flow, where it's basically just a Morse index for a geodesic, for the Euler-Lagrange, for the variational problem for which the geodesics are the critical points. Well, as I already pointed out, they didn't exactly do this work in a vacuum. Colin de Verdière basically had the same results for the Laplace operator, and other people, including Weinstein, who is here. And yeah, all in all, I think it's fair to say that this piece of work was Dijsselmaat's technically most well, complicated piece of work. And to this day, there's no textbook treatment of it. Something that comes closest is a paper which Colin de Verdière wrote in his own Festschrift, where he tries to give as simple a possible proof for this semi-classical trace formula. It's still a long slog, but it may be worth reading also to see what the later developments in this area are. I mean, it's a big field. Another thing I want to pass by you is a paper he wrote on Lagrangian vibrations, fiber bundles. So, a symplectic manifold and a map to a half manifold of n-dimensional connected manifold, such that the fibers are Lagrangian submanifolds of n. So this is what you would get if you have an integrable system with n Poisson commuting variables, and you throw out all the points where the differentials are dependent. And the simplest example of such a thing is, well, when you suppose that your B has a local diffeomorphism into Rn, let's call it P, and let's take this B and let's just cross it with a torus, and let the projection just be the Cartesian projection onto the first factor, and let omega be the standard symplectic form. But typically you call, in this kind of problem, you call the P's actions and the Q's, although I think of them as mod 1 variables on the circle, I will call them angles anyway, up to 2 pi. And you might wonder, is there some kind of extreme version of the Darboux theorem which tells you that every Lagrangian fiber bundle is locally of this form, and the answer is yes. That's the famous Arnold-Liouville theorem. So, and Dijsselbloem looked at what you can say globally. And he found that there is two invariants you can define, which tell you that Lagrangian fibration is globally of this Arnold-Liouville form. Two invariants are called monodromy and the Lagrangian class. Now, the way I wrote the theorem is a bit anachronistic. Dijsselbloem left this Lagrangian class a little bit implicit in his work. This was worked out further later in papers by Zung. Oh, it was Dazot and Delzang who found this class? Okay, so Dazot and Delzang, thank you. And let me just tell you how these invariants are defined. So let's take a point in the base, and let's take a covector at that point. And the first thing you find out is that covectors can be made to act on the fiber. You just pull one back, and then use the Poisson structure to turn it into a vector field. And for every one form downstairs, this gives you a vector field which turns out to be tangent to the fiber. And in fact, this gives you an isomorphism from the cotangent space at the point downstairs and any tangent space to the fiber upstairs. So if you exponentiate these vector fields, you get an action of this tangent space, you view as just an abelian Lie group, a vector group, on this fiber. And this map being isomorphism, that action is locally free. And my assumption was that these fibers are compact, so you see, and connected, so you see there's only one possibility, namely that these fibers have to be tori, n-dimensional tori, the Liouville tori. And they're homogeneous spaces for the cotangent space downstairs, and they become principal homogeneous. So the kernel of the action is a certain lattice in that cotangent space called the period lattice. And when I take all these period lattices together, I'll get something I'll call the period bundle. And when you consider all points in the base at the same time, you might say that this M, this total space of the Lagrangian fibration, is a principal homogeneous space for the cotangent bundle modulo the period bundle, where you view this cotangent bundle as a family of Lie groups, a bundle of Lie groups over the base, with fiber the torus. So the next important observation is that this P, viewed as a submanifold of T star B, is actually a Lagrangian submanifold. So if you take at some point, or if you take a local frame for this P, then, so that's a bunch of one forms, but they're closed one forms because the P is a Lagrangian. And because it's a frame, these differentials are all dependent. So if you locally, in a neighborhood where these forms are exact, you take antiderivatives of these one forms in the frame, you get a preferred system of coordinates on your base. So that shows you that not just that a base manifold which admits such a Lagrangian fibration is a very special beast. There's preferred systems of coordinates, and if you change from one frame of P to another frame, then these two sets of coordinates differ by an element of an affine group with the general linear group, an integer matrix, invertible matrix, semi-direct product with a real translation. So that makes the base manifold an integral affine manifold. And the monodromy is, well, these things have a monodromy associated to them. Basically, that comes from, well, you place yourself at a point. You start with such a frame. You take a loop. And you analytically extend the frame along the loop. Then at the end, it differs from it by one of these affine transformations. And you get the representation of the fundamental group. That's the monodromy. So that really depends. It doesn't depend at all on the symplectic structure of M. It depends only on its period bundle. And you can also wonder what happens if you ignore this translation part. I will call that the linear part of the monodromy. Then you basically get a class which determines up to isomorphism this local system, P, this family of lattices. So if the linear part of the monodromy is trivial, then that period lattice is globally a trivial bundle of groups isomorphic to Z to the N. If in addition the full monodromy is trivial, then globally these global sections of P give for you a system of global coordinates which define for you a local diffeomorphism from the base into Rn. You have a kind of a global chart. Global action variables. And the second part of the invariant. The second invariant, or this Lagrangian class, well, let's first look at a simpler invariant, the Chern class. As you know, a principal torus bundle, P over some space X, has a Chern class, which is in H1 of this base space with values in the sheaf of continuous or smooth functions with values in the group, structure group. And by some easy exact sequence, that's isomorphic to H2 of X with coefficients in the exponential lattice set to the n. And now here we don't have a single group. We have a family. We're dealing with a family of tori over this base manifold given by the Lagrangian vibration. And that gives you a Chern class in H1 of the base with coefficients in a sheaf, which is the sheaf of smooth sections of this family of Lie groups. That's completely analogous to the H1 upstairs. And by a similar argument, that's isomorphic to H2 of the base with coefficients in that local system, the period bundle. So that's the Chern class. If the Chern class is trivial, then this family, then this Lagrangian vibration has a global smooth section. Now, the graph of a one form is Lagrangian if and only if the one form is closed. So it's not too surprising that you can find a finer invariant which will tell you, which will vanish precisely when the Lagrangian vibration has a global Lagrangian section. And that's an invariant. Okay, so it was Delzin and Dazor who defined this. Sorry for the mistake. That lives in H1 of B in a subsheaf of F, namely the sheaf of closed smooth sections. Okay? And that's the two invariants. If those two vanish, the full monodromy and this Lagrangian class, then you have a global action angle variables. And yeah, so I think probably the state of the art in this subject is this paper by Zung. Where he actually takes into account singularities of Lagrangian vibrations as well, and is able to define full invariants for those, at least for certain types of singularities. So Dijkstra detected this monodromy first in Huygens' spherical pendulum. Yeah, that's the particle restrained to a two-sphere and moving under gravity. In the integrable system with the energy and angular momentum about the vertical axis. And the energy momentum map gives you this wedge as a base space, at least part of it. There are singular points, the boundary, of course, and also this point in the middle, which correspond to the pendulum pointing straight up. And here the pendulum is pointing straight down. And this is not simply connected, so he conceivably could get monodromy. And the linear part of it, indeed, is non-trivial. This unipotent class. And it tells you there are no global action angle variables. Cushman and Dijkstra some years later also had a quantum version of this phenomenon, where you just take this same system and just do a Schrödinger quantization, the obvious Schrödinger operator and the angular momentum operator, which happen, fortunately, to commute exactly. And you do a semi-classical analysis, find approximate eigenfunctions, which as Planck's constant approaches zero will become eigenfunctions to order h to the infinite order. And the eigenvalues form what's called this semi-classical spectrum, which you find using some Bohr-Sommerfeld type rules. I'm sorry I don't have a better picture here. If there were global action angle variables, you'd expect some square, like tablecloth-like pattern. But here there's a warp in the fabric of this semi-classical spectrum. And that's the quantum analog of this monodromy. A similar result was done by Guillemin and Uribe. And I think the best current results in this line, along these lines, are by Wu. He has a general theory of quantum monodromy and has, knows how to deal with it in much more general situations. Yeah, I said this would be brief, and it is brief. I'm out of transparencies. I'm just going to stop here. Okay? Good.